So we now get into a class of reactions known as nucleophilic acyl substitution. And this is a class of reactions that actually encompasses multiple functional groups. And we're going to talk about them sort of all simultaneously. And the reason that we do that is because when it comes to acyl substitution reactions, regardless of the functional group that we're talking about, there's only two basic mechanisms: acidic conditions and basic conditions. And everything after that is just sort of a slight variation on those two main mechanisms. But in this section, we're going to see reactions for carboxylic acids, acid chlorides, anhydrides, esters, and amides. So what is an acyl substitution reaction? So an acyl substitution reaction is a carbonyl that has some sort of Y group here. And we can see from the list of functional groups, we've got a number of different options. And by adding a nucleophile, we replace that Y group with a nucleophile. Now, even though it looks like it's a direct substitution, it turns out it isn't, and actually takes place in general in two steps. Because recall that, SN2 type reactions cannot take place on sp2 carbons, and of course the carbon of the carbonyl is sp2 hybridized. So we undergo a two-step pathway where the nucleophile adds, we get a tetrahedral intermediate, and this oxygen could be either O- or OH, depending on our reaction conditions. And then the carbonyl reforms and kicks out whatever that original group attached to the carbonyl was. So the reaction can vary greatly depending on what this Y group is. Some substances, such as anhydrides, an anhydride being an oxygen that's attached to two carbonyls like this, or an acid chloride, very, very highly reactive. In fact, these two functional groups are so highly reactive that while we can easily work with them in the lab, and in some cases they're stable enough that we can store them on the shelf for long periods of time, we rarely find these two functional groups in nature. Whereas the ester and amide definitely less reactive, and very, very common functional groups in nature. But the order of their reactivity is exactly what we've displayed here. Amides are the least reactive, up to the acid chloride, which is the most reactive. So why do we see a difference in reactivity for these different functional groups? What is it that determines that the acid chloride is highly reactive and the amide is much less reactive? Two main factors come into play. One is resonance, and specifically resonance donating ability of whatever this group here is. The second is that same group. How good of a leaving group is it? So how will these two have an impact? Well, if that group there is a very good donor, as an electron donating group, like say the NH2 group is, or whatever the nitrogen group could be is. If it's a very good donor, then it donates more electron density into the carbonyl. If it donates electron density into the carbonyl, then the carbonyl is not as partially positive and is going to be less reactive. On the other hand, down at the other end, chlorine is a terrible resonance donor, and if it's not a good resonance donor, it's not going to help stabilize the carbonyl. As far as leaving groups go, the better the leaving group is, the better the reaction will be. But let's look at that in more detail. So we'll list our 4 groups here again and talk about how these different factors come into play. So how are they as leaving groups? Well, starting on the left with our halogen, we know that most halogens, with the exception of fluorine, are good leaving groups. On the other hand, down at the other end, where we would have a negatively charged nitrogen as the leaving group, or some sort of nitrogen leaving group, it's not always going to be a bad leaving group, because if we can protonate it first and make the leaving group neutral, it's not going to be a bad leaving group, but it's certainly not anywhere near as good as the halide. The anhydride, we have the leaving group here, which is essentially a carboxylate. So it's a resonance stabilized leaving group, also a good leaving group. And then from the ester, we have the OR minus, which is again going to be a much poorer leaving group. What about resonance donating ability? So starting again with chlorine. Chlorine doesn't like to donate by resonance. It's a very, very poor resonance donor. Whereas the nitrogen in the amide, we've seen over and over again in this course that nitrogens are very good resonance donors. Now, both of the oxygens we know can also be resonance donors. They're not as good as nitrogen. But in the ester, that oxygen is donating into one carbonyl. In the anhydride, it's adjacent to 2 carbonyls, and so the electrons on that oxygen are being pulled in both directions. And so because of that, it can't donate as much. And again, that's because there's a carbonyl on both sides of that oxygen, so it's going to be donating maybe not exactly equally, but relatively equally to both carbonyls, which decreases the amount it can donate to one of the carbonyls. That means that it's going to be a poorer resonance donor. And so we can see all the way on the left side, the acid chloride, which we said is a good leaving group, poor resonance donor, has both the features that we want for it to be very reactive. Whereas when we get to the amide, we have exactly the opposite. We have a very good resonance donor and a much poorer leaving group. Now, you might recall that these actually bear some parallels to another property that we saw. Do we remember the IR shifts for these functional groups? So an acid chloride typically shows up around 1800, anhydride slightly lower, lower yet for the ester, and down into the 1600s for the amide. And so what we actually see here is a direct parallel between the wave numbers for the functional group and how reactive it is. The more reactive it is, the higher its IR shift. And that should make sense to us. If you recall, one thing that we talked about with IR spectroscopy was that as those wave numbers went down, we said that that was an indication of less double bond character or more single bond character. Well, we know that single bonds, such as ethers or amines, are not nearly as reactive as carbonyls. And so as we get down towards the ester and the amide end, we've got more single bond character, less double bond character, and the functional group is more reactive.